Start recording. Okay, now we are good. Now we are good. So today we will be looking into principles of counting or into combinatorics. So there are times when we need to count large numbers of things without actually counting them. So we need some kind of shortcuts maybe and so on. Okay, so I won't be doing much of a theory. It will be kind of shorter one today. So let's start with examples outright. Say I have a one coin and one die, and I'm rolling them both at the same time. How many possible combinations are there? We did already look at that. We have this neat table with all the combinations listed. Yeah, we can have either heads or tails on a coin, and we can have any number starting from 1 and up to 6 on a dice.
12?
Yes, sorry?
12?
Okay, so 12, yep, 12 different combinations, and that 12 is in fact 2 times 6. So we have 2 sides for a coin. So coin can come up with any of its 2 sides, and the die can be facing up with any of its 6 faces. And 12 is just a product of those two. And that thing works everywhere. So that's our first rule. Rule of multiplication. A rule of multiplication. So when you have something that can go, that can happen in n different ways, and you have another thing that can happen in m different ways, doing them both, you will have m times n different outcomes. I'm not sure if well, probably not. I don't want to use the mouse for handwriting, so I will just download my transcript, which I posted at the start of the week, and I will just show it from there. But anyway, that's the first rule we can use. So you have one event with n outcomes, you have another event with m outcomes. So the compound event consisting of both will have m times n outcomes. And that's the formula of multiplication, not to be mixed with multiplication rule. We had multiplication rule for probabilities, and we have multiplication formula for counting. Okay. So next one. Let's say I have, I guess you can see the Excel window, right? On your screens.
Yeah, we see it.
I'm pretty sure
Yeah.
that okay. So let's say we have a set of some objects that may be anything. In fact, it might be some things, it might be people and so on. I will just mark them by the letters, and we will choose the simple case. So I have 3 objects. Maybe that's the books. So 3 books, and I want to put them on a shelf, 2 of them. How many ways are there of doing that? So I can put the book A first and book B second. Or I can put book A and book C. Or I can put first book C and B and then book C. And the other way around. So the same combinations but in different orders. And we can see that there are 6 different combinations, 6 different ways to arrange those. It's not totally correct to call that combinations. Yes, Umit? Is something
Sorry, teacher, could you accept others, please? They're
Oh,
just
yeah.
still waiting.
Yeah, I see.
Thanks.
Okay, admitting. Oh, I can swear that one of them is joining like about fifth time in a row.
They have some problems with their network, maybe.
Yeah, we see we have 2 copies of Rabek for some reason. Well, okay, whatever. So we see that there are 6 different ways of doing that, of arranging 2 out of 3 objects. What if we had 4 objects? So let me add 4th one here. So I will also have, it appears I will have something like A and D, B and D, C and D, and the other way around. So DA, DB, DC. Now it's 12. Yeah, it's 12. So we are selecting 2 out of 4 objects and arranging them in different orders. And we have 12 different ways of doing that. I can't imagine any conceivable way of getting 12 from 4 and 2 using just the multiplication. So multiplication formula will not work in this case. We need something else, and we can try to discern, we can try to derive what we need. So let me bring up a whiteboard. I guess it will go all right. So we have 4 objects. We want to choose 2 out of that 4 and place it in different ways. So maybe slightly larger line. So you first you have choice out of 4 numbers. Oh, why is it so transparent? Okay, I guess we can use arrows. That will be better. So you have a choice out of 4. So first position in your arrangement can be any of the 4 objects, right? So you have 4 different outcomes right from the start. So one of them is for A, another one is for B, another one is for C, another one is for D. We are choosing the first object. Then, after you have chosen the first object, for each of those choices, so let's say we choose A to be first. For the second position, we can choose any of the remaining 3, right? We can choose B, we can choose C, or we can choose D. So this branch, our first choice, is branching into 3 additional choices. And that will give us all the arrangements that look like AB, AC, and AD. A first. If we chose B to be first, then for the second one, we can choose either A or C or D. Again, 3 different choices. So this one also branches into 3 different ways. And the same applies to the other one. So if you chose C to be first, then you can choose any of the remaining 3, which are A, B, and D. And if you chose D to be first, you can choose any of the A, B, and C, which are also 3. So you have 4 choices, and after making any of those 4 choices, you have another 3 choices. So the total number is 4 times 3, which is which is 12. And we know that it's indeed 12 because we made a full list of that. So let me close the whiteboard and go back to our Excel. However, what matters is this 3 here, or maybe, yeah, I won't close it for now. I'll just switch to Excel and then maybe we will be back here. Maybe. So where is Excel? It's here. Okay, so we have these 12 different arrangements for 2 out of 4. What if I was going to choose 3 out of 4? Then I will have something like ABC or ABD or ACD or ACB or ADB or ADC. That's when A is first. And then I have B first. So I can have BAC, BCA, BAD, BDA, BCD, BDC, and so on. And well, we can go like that, but it will take some time. So I'd rather apply something like that tree picture we did for this. So for first position, so if I'm choosing 3 out of 4, for my first position, I can choose any of the 4. And then for each of those choices, I can choose any of the remaining 3. And then after that, I will choose any of the remaining 2. So the total number should be 24 in this case. And we can check that. So we can just go all the way and do DAB, DBA, DAC, DCA, DBC, DCB, and so on. And I guess you are seeing where does it lead. We will have the same thing with C, CAB, CBA, CDA, CAD, CBD, and CDB. So that's all the arrangements of 3 out of 4. And okay, so there are 6 rows and 4 columns, so it's 24. And I'm starting to see the pattern here. So here we had 4 times 3. And here we have 4 times 3 times 2. What if I want to choose maybe 2, or not 2, maybe 4 out of 7. So for my first position, I can choose any of the 7. For the second one, any of the remaining 6. For third one, any of the remaining 5. And for the fourth position, any of the remaining 4. And that will give us the total number. That will be a large number. So let me calculate it quickly. I'm a lazy person and I will just use calculator wherever that's possible. Okay,
840.
840 different combinations. So lucky for us that we didn't try to do the listing like this. That will fill all the screen, and that will use up all of our time. Well, okay, nice, but how can I formalize that? So how can I turn it into neat little formula? So let me try to write it like this. So I have here, I will take this and, well, let me just copy. So yeah, however, I will get rid of that equal sign. I will do it like this. So I will multiply it by 3, by 2, and by 1. And then I will divide it by 3, by 2, by 1. So that's the same number. 3, 2, and 1 cancel out, right? And we will only have 7, 6, 5, and 4 remaining. But now in this form, it looks kind of neat. Do you guys remember what the factorial is? So there is a thing called a factorial. We denote it by exclamation mark. So for example, if you see something like 4 factorial, it means you take 4, you multiply it by 3, by 2, and then by 1. And that's the 4 factorial. So it's 24. Or if you have maybe 9 factorial, it just means you take 9, you multiply it by 8, by 7, by 6, by 5, by 4, by 3, by 2, and by 1. So here we have 7 factorial in the numerator, so 7 factorial, and we have 3 factorial in the denominator. And if we look even more deeper, this 3 is in fact 7 minus 4. So 7 factorial divided by 7 minus 4 factorial. It looks like we have a formula. So the number we are looking for, number of arrangements of m objects out of n, should be this one. Let us check. So 3 out of 4. I should have 4 factorial divided by 4 minus 3 factorial. And that's just 4 times 3 times 2 times 1 divided by 1. And it's 24. And yep, we know that it's 24. So it looks right. Let us check it here. 2 out of 4. So we should have 4 factorial divided by 4 minus 2 factorial, and it's 4 times 3 times 2 times 1 divided by 2 times 1. So that's just 4 times 3, that's 12. We have our formula. So that thing is called number of permutations. So permutations of m out of n. And in fact, so let me move to our transcript. Here it is. Here, the permutation formula. This neat thing. We denote it by P. So n is the total number of objects, and m is the number chosen. So how many we are taking from that total number to put into order. Well, one example might be choosing employees for positions in your company. So you have a small company of 15 people, let's say, and you need to have a CEO. You need to have maybe the accountant, and maybe you need to have a president of a company. So you have 3 positions which you need to fill in. So you have to choose 3 people out of those 15. And the order matters. So let's say, for example, you have an employee, maybe John Smith. You can put John Smith either in the CEO position, or in the president position, or in the accountant position. And that's the different choices. So you need to choose 3 people and then put them on the corresponding positions. And that will be just the number of permutations for 3 out of 15. And we can calculate that. And also, so whenever you are using something like Excel, you even won't need to memorize that formula, because let me go back to our Excel here. Oh, I need to stop annotations first. Because Excel has the inbuilt formula for that. So there is a permute. That's a number of permutations. So first one is our n here. So let's say we want to find the number of arrangements, number of permutations of 4 out of 7. So I will put 7 first and 4 second. And the Excel will calculate it for us, and it's indeed 840, as we have already seen. Okay, good enough. But there are cases where you do not.
How did you get 800?
Sorry?
I didn't see this line. Could you repeat, how did you get 840?
This one or this one?
Yeah, 840. No, no,
So
no.
here I just used that logic. And here I just used the inbuilt Excel formula. Permutations of 4 out of 7.
Okay, got it.
I can't see you quite clearly, guys. Oh, I can hear you clearly. I mean, anything else?
Oh, that's okay.
Okay, nice. So that's the number of permutations. That's when you have to choose a number of objects from a common pool, and the order of that choice matters. So like here, for example, these two cases, we have the same objects chosen, A and B, but they are in different orders. Or like here, you have ABC, you have BAC, and you have CBA, and CAB, and ACB. So the same objects, but in different orders. And when the order matters, you use permutation formula. So I won't switch back to the PDF, but you can go to the announcements and there is a transcript and the formula itself is there. Okay. And there are times when order does not matter. So let's say I want to, so I come to the shop, maybe I come to the bookshop and they have something like hundreds and hundreds of books there, and I want to buy 3 books at once. And it doesn't matter in which order the seller will give them to me, because the result will be the same. I will have 3 books I want. So again, let's go back to this, for example. Yeah, let's imagine a very bad, very poor bookshop which has only 4 books on sale, and I want to buy 3 books, and I buy the book A, book B, and book C, or I buy the book C, book A, and book B. Is there any difference? The difference is just in order. So maybe I will put the book A into my bag first, or maybe I will put book B into my bag first, but in the end, it's just the same thing. I have the same 3 books, and in this case, order does not matter for me. So from that perspective, ABC and CAB will be the same choice for me when the order does not matter. And in this case, we need to account for repetitions, let's call it that way. So like here, for example, we have AB and BA, which are the same thing if we are not interested in their order. So in fact, when I'm counting all of them, when I'm using permutations formula, I'm counting this AB and BA as 2 different cases, because they are 2 different permutations. So let me write it down here. They are different permutations, but they are the same combination. And if I want to, oh, what did I do wrong? Oh, okay. So Excel thought that it's a formula instead of a text. Oh, sometimes it drives me crazy. Sometimes it makes me go nuts. So let's try now. Okay, so these two are the same combination, but they are different permutations. So we have two permutations here, but one combination. So if I want to find the number of combinations in this case, I need to, so let me put it this way, number of combinations. I need to take the number of permutations and divide it by number of, well, what do we call that? So in fact, that's also called permutations, but it will be unintuitive here. So I will just write, I will use number of repetitions. So in some sense, the same combination A and B is repeating here, just in different order, creating the different permutations. Okay, and in this case, I know that each of those combinations are repeated 2 times. So I have AB and I have BA. So if I want to find the number of combinations of 2 out of 4, I will take the number of permutations for 2 out of 4, which is 12, and I will divide it by 2, and that's just 6. We have A and B, we have A and C, B and C, and so on. What if I want to look at 3 out of 4? So again, let me bring this table here. And let's spot the same combinations. So this one, and this one, and this one, and this one, and these two are the same. So I will colorize them. I guess that will be all right. Oh, what's up? Aha, okay. So let's paint them yellow, maybe. Those ones. 2, 3, 5, and one more here. So we have 6 different arrangements, 6 different permutations for the same combination. And then we have this. And again, I will go on and colorize it in green. ABD, ADB is the same. And here, these two. And these two. Again, 6 of them here. So when we are choosing 3 out of 4.
The teacher, a student is waiting for your acceptance.
Oh. Okay, just a moment. Okay, admitted. Is there any way to make it like auto admission? So instead of going to the waiting room, they will come straight into the conference itself. If any one of you knows something like that, let me know, please, because sometimes it gets kind of distracting.
Some other subjects we do not wait. Maybe.
Okay, I will try looking that
maybe
up.
you should ask.
Yeah, I guess yes.
Some
I remember in the spring it was same way for me. There was no waiting room, and I tried turning off waiting room on our previous lesson, and then one of you was just unable to join. But okay, we will see. We will see. Maybe I will go and do it right now, but yeah, whatever, later. Okay, so here, each permutation, each combination is giving rise to 6 different permutations. Yep, we can see that the symbols are the same, the objects are the same, just the order is different. So if I want to find the number of combinations of 3 out of 4, I should take the number of permutations, which is 24, and divide it not by 2 this time, but by 6, because each combination is repeated 6 times. And if I look at something like this, oh, that will be a hell of a job to do. But just believe me, maybe you can try it yourself as your homework, trying to find a number of different arrangements of 4 symbols. You will need to take that number, which is 840, I guess, yeah, and divide it by 24, because when you are choosing 4 objects, each combination will give you 24 different permutations. Okay, let's not be lazy and do that. So I will, so ABCD, ABDC, ACBD, ACDB, ADCB, and ADBC. So that's all the cases when A is first. And then, so there are 1, 2, 3, 4, 5, 6 of them. Then you will have 6 for B first, and 6 for C first, and 6 for D first. So 24 in total. And some of you might just stop me here and say, but teacher, 6 is just 3 factorial. Oh, sorry, 2 is just 2 factorial, and 6 is just 3 factorial, and 24 is just 4 factorial. So in fact, what we are doing here is we are taking a number of permutations and dividing it by the factorial of number of chosen objects. So if we go back to this formula, I can do it like this. So we divide by n minus m factorial and also by m factorial. So let's check. Let's take 3 out of 4. So I will have 4 factorial divided by 4 minus 3 factorial and 3 factorial. So that will be 24 divided by 1 times 6. And 24 divided by 6 is just 4. So 4 different combinations. We can list all those combinations if you want. So that will be just ABC and ABD and ACD and BCD. That's combinations, not permutations. If we were counting permutations, we would also account for something like CBA and CAB and so on, which are the same combinations but different permutations. Okay, so that's number of combinations. And again, that same formula is there in our transcript in a neat and good looking way. So here it is. So we denote number of permutations by P and number of combinations by C. And that's just the same thing that's there in Excel. Okay, Excel has inbuilt formula for combinations too. So it's just combine. And again, first you put the total number, maybe 4, and then you put the number chosen, 3, and we will get 4, just like we should. or if you want, we can take this example. So 4 out of 7. So again, let's make Excel calculate that. 7, 4. And that's 35. And if we divide 840 by 24, we get 35. So everything's right. Okay. So let's go back to our previous example. We were choosing 3 guys out of 15 to be a president of company, a CEO of company, and an accountant of company. And we were counting different ways of doing that. What if we were choosing 3 guys to go for a work trip? So we just need 3 guys who will, I don't know, who will fly to Mongolia to learn something new, and so on. In this case, we don't have any positions. We just need 3 people, and it's the same case as here. The order does not matter, and you will use combinations, combination formula instead of permutation formula. So they are almost the same. Permutation formula and combination formula are about the same thing, about choosing part of the set. But in case of permutations, the order in which you choose them matters. And for combinations, it does not. And that's the only difference. So let's take a break for maybe 5 minutes. I won't stop the conference, just so that you guys and I can, what do you call it? Empty our heads, get a bit of a fresh air, and then we will continue with the topic. We will see some examples of usage of that in probabilities. So it's 2:43 on my clock. So then see you in 2:48. Okay, 2:50. Be right back.